These techniques and the calculation I'm showing in the notational wise looks a bit scary, but you better get used to the sigma manipulation. This is what I call, and many students try to avoid it. But when you get used to sigma manipulation in the Taylor series and differential equation and all the other science and engineering measure, you have an additional extra power. Just like you can do algebra versus someone there who can't really do algebra but kind of understand how the mathematics goes. Is that much of a comparison. So you're always busy and try to stay away from anything that is difficult, but learning the sigma manipulation is a good thing. It's just like integral idea as well. So first here we write down sk and j going from 1 through k of j times j plus 1. Is that right? Okay. So I want you to look at we're about to calculate this one. They're a very, very small class of example. You can actually calculate this thing, just like integral. If it is integral 1 divided by x times x plus 1, how do you integrate that? You change that to integral and then to 1 divided by x times x plus 1. What technique do you use to integrate that? Remember those? Partial fraction decomposition. Right? So here's a j, 1 over j, j plus 1. You thought it's gone, it came back, right? So how does that work? J and j plus a linear factor, they have no common factor, right? So they split it. Is that right? Like that? And how does the numerator look like? This is degree 1 and degree 1. So it should be degree smaller than 1, which is constant a and b. Correct? So this one splits like this. Partial fraction decomposition theorem. Okay? So let's go ahead and do that. Denominator is going to well match up. So numerator, left-hand side is 1. We don't have to plug in anything. It's always 1. But what about the right-hand side? A is multiplied by j plus 1, correct? And b is multiplied by j. We've got this one. And what do? We have this specialization technique, right? So what do we plug in here? When j is 0, right? Left-hand side is 1. Is that right? There's no j in the left-hand side to plug in. When j is 0, that's gone. So a is 1. That's what it says. When j is what number is the next number we try? Negative 1. What happened to the left-hand side? Constant 1. This disappears and negative b. That tells you b must be negative 1. Correct? So we have a calculated as 1 and b calculated as a negative 1, right? So it's like the integral that you look at in here, j going from 1 through k. And this one is j in the numerator 1. Split it 1 and j plus 1. Because negative 1 and write it like this. Okay? If this is an integral, you can split that integral, right? And then calculate it like log j, something like that. Isn't that how you integrate? Yeah. So you split it just like the integral. 1 over j minus j going from 1 through k, 1 over j plus 1. The reason it splits is exactly the same reason that integral splits. So Riemann sum. Sum of things, you can just split it. All right. Do you agree that the way it looks like is 1 over j and 1 over j plus 1 looks a lot like it? This is going through 1 through k. This is going through 1 through k, but it's starting from 2 to k plus 1. The only thing is it's going to cancel a lot. This, if you list them down, 1 and 1/2 and 1/3, this one starts at 2, 1/2 and 1/3 have a lot of overlap, right? So you can actually list them down and kind of cross it out. But I like to introduce something called reindexing, or in integral formulation, it's called substitution rule. You substitute something. So what is our u substitution? Is this j plus 1. Then this one looks a lot like 1 over j, like 1 over u, right? So these are just the dummy index variable. So I'm writing it again. 1j going from 1 through k, 1 over j minus, Now everything changed in terms of u. When j is 0, when j is 1, that's the initial number, what is the u value start? Like the integral. 2. You start from 2. When it's ending at k, j value of the k, what is the u value? It's k plus 1. Is that right? It's 1 over, the whole thing is u. There is no reciprocal multiply or anything in here. Simple substitution and reindexing, and that's it for the sum. All right. By looking at these two things, this one starts 1 through k, but this one looks exactly the same from 1 over u, but it goes through 2 to k plus 1. Right? So is that okay if I write this one down again like this? This could be sometimes a difficult step to understand. 1 over j is exactly like that. This second term, u, is a dummy variable, just index, right? So can we just change it to back to j again? And if you think about the meaning of this one, that's exactly the same thing. You start from 2, go all the way from k plus 1. Doesn't matter which variable you use because they're separated. One term over there, sigma is only affecting the first term. Second term over here, this sigma only affecting the second term. So this dummy variable can be used after you separate it. Done through it. Does that make sense? Yeah. Let me write down here again. U going through 1 through 3 of u versus j going from 1 through 3 the j. These two things are the same. 1 plus 2 plus 3. Right? J going through 1 through 3 is 1 plus 2 plus 3. Although it's denoted different, what is representing is exactly the same. Okay, well, once you reindex it, it looks in the kind of same shape, then you can change the variable. Now you look at the common index. It goes 1 through k, this one 2 through k plus 1, right? So what's the common index? This one has a 2 in there, right? All the way up to k is in there, but it goes a little bit more than k. So 2 to k is a common index. Is that correct? This one index is going through k, 1 through k and 2 through k plus 1. Therefore, common index is 2 through k. Right? So you split that each of the term into common index. So this one has 1 through k. Common index is 2 through k. So why don't we write it like this? 2 through k, 1 over j. But wait, this one actually starts from 1 through k, and this one only covers from 2 through k, so you've got to have 1 over 1 in that outside, set aside, so that it matches the first term. Make sense? Yeah. This one only covers 2 through k, 1 through k. That one is coming from j equals 1. So next term, j going through 2 through, what was the index there? K going k plus 1. The common index stops it right there, the k. So you write it 1 over j. But it goes all the way up to k plus 1. So you've got to have that and set aside that term k plus 1 out here. So I'm going to box it. The sigma only affects this 1 over j, and this one is set outside. You see why these two things are equal to each other? You looked at the common index, and whatever that doesn't fall into that common index is written explicitly outside. By doing that, this common index is cancelled out. Negative, negative. So you're just leaving only u, that 1 over minus k plus 1. So for that special example, we were lucky. We started with this crazy example, and we're able to calculate the closed formula of the partial sum, right? What's the partial sum? 1 minus 1 over k. So if you go in here, and if you plug in 10, whatever, you got 0.888. That's if you plug in 3 something, you get that number exactly. Okay? So, but what does everyone want to prove? What happened to this partial sum, right? Where is this partial? As you add more and more term, and where's your final destination as you walk, and then it's clear as k goes to infinity, this one is 1, right? So from that observation. So we proved it. This the sigma calculation and all the technique you use for integral calculation is considered equivalent. Here's another example.